All right, welcome back. So we know that row operations, these powerful things we have, tools we have, can give us the inverse of a matrix A, which we desire so much with our heart. All right, so a couple of things. There's a picture of a cat here for some reason. So this is just going to be looking more deeply at those row operations and bringing elimination matrices in and showing how we get a more powerful story. Yeah, a couple of things come out of this. So we're going to connect it to elimination matrices. We're going to look at inverses of elimination matrices, and we'll sort of just talk our way through that. And you should see that they're very simple. It's a very nice thing. It's a very important thing. So that's the first couple of pieces. More on why missing pivots and inverses not existing is a story. This is our cat Pratchett. He's very excited about inverses, matrices in general, as long as there are treats involved. And then I'll add a little bit about columns. So let's get through this. So this is a little bit more theoretical, but we'll connect a few things. So the first thing I was going to talk about is, okay, so we've got this example we've been working on. Right, so we have A equals 3, minus 2, minus 2 and 4. Something I haven't said, this is going to be an important thing later on. This is a little aside. I can't help myself. So this is an aside. A equals A transpose. Right, that's T for transpose. We're about to get to those things. So if we swap here, if we take this matrix and swap everything around the main diagonal, it looks the same. They're going to be kind of the best matrices. All right, I'm being Boxist, I guess, but that's they are pretty amazing, and we can always make one out of any other matrix. So there you go. That's why it's okay for me to say that. So the inverse we found the right inverse. So we're going to make sure that that's absolutely true. That it is also the left inverse. Super cool. Also symmetric. I'm just a little foreshadowing. So A to the minus 1 is transpose is also equal to A to the minus 1. So if we swap that, so it's really for 2 by 2s, it's just that the off diagonal is the same. Okay, so we've got these things. Let's talk about how we would go about this with elimination matrices. And well, we did all the row operations, right? So they're back here, right? There were 2 row operations. This one, and then this one, and then we divided through by the pivots. So we need to do 3 things when we turn this into elimination matrix action. So I'm just going to write them down, and you can go and check that they're the same thing. So let's row reduction. Let's replace that with elimination matrices. So the first step would be, so we're trying to solve, we're solving, all right, for solving this augmented matrix problem, right, which is A times Z equals I. And then that Z, we believe, will be the inverse of A. All right, so the first step was that there was we're adding 2/3 of the first row to the second row, and the way that will work, so let's just write them down. So E21 is equal to, and it's always the multiplier sitting here. So let's just identify those things. So this is row 2, this is row 1, and this is minus L21. Did I get that right? Screw it back over here, yeah, right. So L21 was 2/3 here, and that's our gain, right? Okay, good. Right, elimination matrices always look like the identity matrix with just one multiplier in there. So if it's E73, that's multiplier L minus L73 with a minus sign. Confusing. So that's E21. That's the first row up. So this is row up 1. And then row up 2, can put it here, I think. Row up 2 was this, would be encoded with this matrix. E12, right? We're getting rid of the entry in row 1, column 2. Again, looks mostly like the identity matrix, 1, 1, 1. We've got a 0 here, and we have an entry up here, which is 3/4. This is plus, this piece in here is plus L12. Well, it's not L12, right? We're not going to, okay. I'm not going to use that same notation. That's a bit unfortunate, isn't it? All right, but it is the multiplier that we used. Okay, that's 2 of them. And then we had to divide through. So this is an interesting thing. We had to divide through by the pivots. So we're going to do something slightly, let's write down the pivot matrix. So pivot matrix. So we're putting our components together. A pivot matrix was 3. So we're just putting the pivots in. Let me write it like this. It's D1, whatever the pivots are. Doesn't matter how big it is. It's a diagonal matrix. And it's 3 3/8. Is that right? 8/3. Now diagonal matrices, their inverses are easy. So d to the minus 1 is equal to 1/3, 0, 0, 3/8. And you can think about this in lots of different, I mean, you just simply multiply them together, right? The third comes through and just hits the 3. That's the only time it gives you anything. You get a 1. The 3/8 does the 8/3. But a nice way to think about it perhaps is, what does this matrix do when it multiplies something? It says I want the new row 1 that I'm creating when I multiply something on the right will be 3 times the old row 1 plus 0 times row 2. So it's just, let's just triple the first row. This says multiply the second row by 8/3. That's what it does. And then this one says divide the first row by 3 and then divide the second row by 8/3 and flip them upside down. So they undo, right? They undo each other. These undo each other. Right, that's perhaps a good way to see it. Okay. So our series of row operations for which, so we went from, in transforming 3 minus 2 minus 2, 4, 1, 0, 0, 1, right, to the format we wanted, which was, it's going to be the identity matrix here. And then we had these things. We had a half, a quarter. Do that again, I guess. A half, a quarter here as well, and 3/8. Right, that's a to the minus 1. It's the same as doing this to a, right? So these row operations are the same as doing E21 first on a, and then let me write it like this. Here's our original equation. A times z equals I. What we're doing is the first row operation, it's E21 multiplied by on the left. We're doing that to both sides. The next row operation, it's E12 both sides, E12. And then the last one is we divide through by the pivots. So this is much more powerful, right? Instead of this sequence of written instructions, we now have a nice matrix operation. This thing, right? Any matrix times I is just that matrix. This is what we showed to be the inverse. So this is great. That's the inverse. And it's sitting here on the right-hand side, so this is the inverse as well. Right, so all of this times A gives us just the identity. So what's happening? This is identity times Z. And that has to be the inverse as well, right? That's from here. This is from here. So the thing we uncovered through row operations, this is found by row operations. found by row operations. Right, by uncovering, at the same time, we are, this is actually also made by elimination matrices, by the E matrices, E and D matrices. Let's put an IJ there. So there are two ways to get to them. They equal each other. We'll come back to that. Yeah, this is an important thing that we have done. Right. The next thing is to see how the inverses of these matrices work, these elimination matrices. So let's do that next. All right. So this is a big deal. Let me just write it here. So big deal is we see a to the minus 1 is a product of the E's, EIJs, the D matrix, D pivots, the inverse of that. Pivots are in here, and then potentially this as well. We need to keep this as a permutation matrix. We don't talk about it too much, but you may have to for row swaps. So there may have been some row swaps going on. That also, I'll pop that back in now and then, but that's, yeah. Okay, good. So that's a big deal. All right, so next plan, the next plan is this, is the B, elimination. So did I write that there? So, okay, so next, we see that the elimination matrices have simple inverses. They're simple little algorithms. Matrices have simple, so exciting, I know you're just pumped, simple inverses. So if we had, say, E31, let's say this is a 3 by 3 problem, it all looks like the identity matrix, and then maybe it has a number here, so this is -2. So what is this thing doing? This says this is equivalent to saying row 3 prime equals row 3 minus 2 times, minus 2 times row 1. Right, that's equivalent to that. Yeah. So how do we undo this? Undo. So say we've done this to a matrix, right? We've taken its new old row 3, subtracted 2 times row 1 from it, and made that the new row 3. Undo with, simple, because we haven't changed row 1, it's still there. We can say, let's just add back 2 times row 1. Right, and the primes right, so if we did this, and then we did this, if we do this row operation, then this row operation, that will undo the thing. So E3 minus 1, the inverse of it, this is a pretty big deal, is equal to 1, 0, 0, 0, 1. All looks the same. And then there's just plus 2 here. We just swap the sign. Swap sign. So that's going to be true of all of these things. If you want, you can multiply these guys together, and you should see that that will work. So that's a good check. Check. E31 times E3, what we're claiming to be 3,1 minus 1, E31 equals the identity. But we've just sort of argued how it must be the case that these things work. They also have, if you did row reduction, right, you could get rid of this character here on this. You can see it has 3 pivots, 1, 2, 3. It's a healthy matrix. It doesn't have any of these problems with missing pivots. Yeah. So that's the general. So this is the general. So in general, flip sign of off-diagonal element to me. Those things of off, there's just the lone off-diagonal element. Off-diagonal, right? This is diagonal, this is off-diagonal element. To turn Eij into Eij minus 1. Right, so we have to. Okay, that's a good thing. And the last thing perhaps to add here is, let's do this here, is that this is, the way this works, this is minus L31. So this is plus L31. So this is really why we put a minus sign in our row operations. It's because later on when we get to these inverses, which we'll then build to make some other matrix, we get plus signs. So this is really, let me link to this. Monks made us do this. Right, yeah, that was the plan. Sneaky plan. Okay, lots of sneakiness. All right, so that's pretty good. There's also the inverses for the permutation matrices. So permutation matrices. Let's just quickly say what that is. So here's one example permutation matrix. So it's 1 0 0 0 0 1 0 1 0. Right. So what this encodes is row 1 prime is row 1. Right. Don't change it. Row 2 prime is row 3. Right. We're actually going to pick up row 3 and put it into row 2, and we're going to swap. So you should be able to kind of make little gadget matrices like this for yourself. Really become familiar with it. The new row 2 is the old row 3. The new row 3 is the old row 2. Good. So how do you undo that? Well, you just have to swap this back here. So in this case, p to the minus 1 is actually here, is the same thing. You just permute it again here. But in general, P inverse is P transpose, which is true here too, right? So if we swapped, I know I'm kind of introducing that term, so if we swapped it around the diagonal, we get the same matrix back. So it's a transpose of P. We could prove that a little bit later on, but I'm just going to say it here, I think is the plan. Okay, that's good. So just a couple of things. A couple of things just to add a little, let's see, just a little bit to add about non-pivots. So pivot issues, pivots, missing pivots. Sorry about that. Yeah, okay, missing pivots. The cat is ridiculous. Okay, so let's just say, okay, so we're doing our row reduction, right? So we've got A, I. What if, let's sort this. So what if A to the minus, A, this thing we work on, right? The giant augmented matrix leads to one or more rows of zeros. On the left, right? So there are missing pivots, in other words. So missing pivots. Missing pivots. So we know we're in trouble in a number of ways. the way to see, so there are a couple of ways to see this. So, so from before, we had that if x not equal to 0 solves, if there's one of these, and there will be infinitely many, equals 0, then a to the minus 1 cannot exist. Right? That was a proof by contradiction, right? So this is from before. So we had that. And this matches up with having missing pivots, right? Because we know in that case, so if we do row reduction, right, so here's the problem. So if we solve this problem, right, so we do row reduction on A, go back to the normal, right, so this thing, we solve, we can always get to an upper triangular, right, so we go with row operations, row ups. If you do row operations on this, then 0 never changed, right, this is still 0. This is B in this case. Then we'll get to U. This is upper triangular. Triangular. And on the right-hand side, we'll get 0. And this is actually C, right? Right. There's no 0, so no non-zero things can be produced here. And if we have a row of zeros, so the plan is if we have a row of zeros here, so row of zeros in U, then that means we'll have infinitely many solutions. Right. So a solution exists, right? Which means a to the x equals 0 is solved by, I mean, obviously 0 works, but is solved by x not equal to 0, which because of our little result before, which means a to the minus 1 does not exist. Okay, fine. So I'll give you a quick example. Let's just say we have this one. So what if we have 3, 2, 6, 4? So this is a little example. So we do one simple row operation. I'll just do a quick. So row 2 prime equals row 2 minus 6 over 3. Same thing. So the pivot is here, 3 times row 1. So we do that one step. It's 3, 2, 0. Top row doesn't change. Second row was a multiple of the first. All zeros. So missing pivot. Missing pivot leads to a row of zeros is pivot. Infinitely many solutions. Right? You need to have a full set of pivots. So let's have a little bit of an upshot here. Yep. A few things. So a to the minus 1 exists. This is the same as equivalency saying A's pivots. A has, let me write it like A has n pivots. And A is an n by n matrix. All right, so it has n pivots. None are missing. That's the way to say that. It also means that Ax equals 0 has only x equals 0 as a solution. I know, it should be more fun, right? But it is fun as a solution. It's just all of these things will fit together as a solution. Concentrate. And incredibly, this is for square matrices. that the determinant of A, which we've talked about just a little bit, is not equal to 0. Weird. So this is for later. That's a crazy thing. And something to do with rectangles and parallelograms. Parallelograms will be involved. And parallelepipeds, which was made up by someone with a particular linguistic cruelty built into them. All right. I think that's it. This is just a number of things to connect. There'll be more of these sorts of things to connect, right? This is sort of a cool, groovy thing. Let's put a box around it. If I can do that. Woo. Oh, no. I don't know if I can. It's going to be too technically difficult for me. Surely not. Look at that. Okay. That's good. I think we have from back here this result that if we do our row reduction, we create the inverse, as long as we've got n pivots, we create the inverse on the right? That's how we find it here. That's what this is showing. And on the left, we see that this undoes A as well. So we have this construction, right? The pivot, the inverse of the pivot matrix multiplied by the elimination matrices, potentially a permutation matrix. All of those things combined give us an inverse that works on the left and the right. Okay, so this is let me sort of annotate here. So this is a and I want to add here plus this. This is a proof, or demonstrates, I should say, right? Demonstrates that the method we're using, that A to the minus 1 is a left and right inverse. It's a proper inverse, right? So our procedure, right, as determined by row operations. It's a big deal. That's good. Huge. Huge. I think that's what I need to show you there. And then there's one more piece here. Let me just allude to, just kind of get this going. So this is an interesting thing. And this starts to kind of show you the strangeness, perhaps, of some more strangeness, right? So if A, so let's go back to A, has column 1, and let's say it's a 3 by 3. It doesn't actually matter, it has a column 1 plus column 2 equals column 3. Right, so the first column plus the second column equals the third column. Show, it's kind of strange, show A to the minus 1 does not exist. Weird. Which is, so another way is that there's a missing pivot. And one way to, so one way to see this is so we can see that A to this A times this vector, 1, 1, minus 1, right, equals 0, 0, 0. Because what does this say, right? This is the column picture. This is 1 times A1 plus, so the column picture. 1, this is a 3 by 1, right? It's the first column of A, plus 1, this is cool, minus 1 times A3 equals 0, 0, 0. And we're being told this, right? We're being told that column 1 plus column 2 equals column 3. So column 1, what this is column 1 plus column 2, and then we're subtracting off column 3. So that has to equal 0. So So we see this. So this is a non-zero solution. So why do we do this? This is a non-zero solution to the problem ax equals 0. That's a big deal. So ax equals 0, just to say it again and again, this is a really fundamental equation. Ax equals b, important in general, but ax equals 0, super important. So that means a to the minus 1 does not exist. From the arguments we gave before, and that there's a pivot missing. So this is one thing to see here. Another is perhaps another dimension, right? Another aspect. When we do row operations, so row operations destroy the rows, right? So row operations destroy rows, right? They mess with the rows, the contents get messed up, but they don't change the relationships between the columns, right? But the column relationships are unchanged. So if we do row reduction, this is a funny thing to see, but if we get down to here, so row reduction gives us this. So there's going to be some blob here, some blob here. I'll put an apple here, right? A blob. There's something on fire. A little campfire. Let's just make a campfire. So we could get to this. The first two steps would give us, the first three steps would give us this. What I'm saying is that the column relationships will still be the same. So we'd still have column 1 plus column 2 equals column 3. And this means that 0 plus 0 has to equal this number here. So I should call that something. Yeah. Right, so this is, yeah. So this is a little squircle. And so that little squircle equals 0 plus 0, which, as we are familiar with, is 0. So this would mean this is a missing pivot. So that fits again, right? So this must be 0, which means third pivot has gone missing. And there's a case for Hercule Poirot, if he is so inclined. Pretty interesting, right? So you could try this if you want. 1, 1, 1, and then let's make a 2, 3, 4. So this is A1 and A2, and we want the situation where they add up to give you the third, so A3, and in this case, this is equal to A2. I should write A1 plus A2. Yes! All right, so that thing, if we did row reduction, let's do a little row reduction. I'll skip a little bit. So you can do a couple of row operations, right? We could clean this up. We're just going to subtract row 1 from the first, from the second and third. So we're just subtracting that off. 2, 3, oops. So yeah, so that's a 1. 4 minus 3 is 1. And then we get a 0 here. 4 minus 2 is 2. 5 minus 3 is 2. And if you look at this, let's just look at the columns again. So column 1 plus column 2. So 1 plus 2 is 3. 0 plus 1 is 1. 0 plus 2 is 2. So it's still, right? Still the same. Col 1 plus col 2. Col 2 equals col 3. And then we do one more row operation, and I'm leaving out the details, blah, 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 blah. And so this would be 2 times the second row from subtracting from the third, and here's our stair step, and this is still true here, right? Column 2 plus column 1 is column 3. And we got our missing pivot. So this is linear dependence. Columns are linear. This is something that's going to be huge, right? So they're linearly dependent. One of them can be expressed in terms of the others, at least, or we could flip that around. Okay, so that is connected to, this connects to many interesting things. And this is for square matrices, but we'll see it for rectangular ones not existing. And all of those other results. Missing pivot, determinant is 0, right, good. Okay, so that's a little bit of mysteriousness there, but hopefully it's interesting. And it will come back. So it's good thinking, it's good knowledge, it's always good knowledge, everything is good, more to come. Okay.